Good evening. Last time I spoke in detail about the design on this flowchart, the first really general reinforcement learning system. Last week I spoke about the general method for heuristic dynamic programming to adapt a critic network where the function you plug in could be a matrix or a neural network or anything else. In my papers defining heuristic dynamic programming, since the late 1970s until now, I have consistently defined heuristic dynamic programming as the general method. And so in the Handbook for Intelligent Control, I suggest if you start to develop general purpose user software for ADP, the program for HDP and BAC should be very general, and they should be able to call on any subroutine for which there is a dual subroutine. The user should have the choice of what kind of model to use because the algorithm is very general and can be applied to any algorithm. But today I'm going to be going deeply into the neural network special case. One of my motivations here is to understand how do brains work, and they would fill in all of these boxes with neural networks to be adapted concurrently. Again, you can stick in any model you want in here and a neural network up here. That's your choice. But for this initial design, I was considering how can you build a neural network learning system, a brain-like system, where you fill in all three boxes to be learned concurrently. So today I'm going to be talking about neural networks, about backpropagation, how we calculate those derivatives, and how we develop those dual subroutines. As usual, I'm going to start out with the big picture and show you where we are in the big picture. I'm going to be talking about neural networks, and I'm especially going to be talking about this equation down here at the bottom, which is the chain rule for ordered derivatives. In general, this slide describes what I think are the 5 most important new research directions within the neural network field in general. There are applications trying to use new mathematics to improve the chances of human survival on Earth, humans going into space, and understanding the human mind and human potential. Those are all very important application areas, but I won't be talking about them today. I'll be focusing on the left-hand side. I've already spoken about the Bellman equation at great length. I'll speak about it more. It's absolutely fundamental to what we're doing in this course. But to implement the Bellman equation, to build complex learning systems, it's also very important in the end to understand all of these things on the left. This week I'll be talking about this chain rule for ordered derivatives, which is backpropagation, which is how we calculate the derivatives. Next week I'll talk a little bit more about Bayes' law, which is important to statistics and important to how we train model networks, how we do prediction. Let me say as a quick starter, if you look up the word backpropagation, unfortunately what you read out there today is very, very spotty. I have to confess I've read some things in places like Wikipedia where they tell you about backpropagation, and you can tell that the people who wrote the article do not even know what backpropagation is. Today I'm going to be telling you what it is and where it really came from, and unfortunately I have to dispel some of the myths. I don't like to dispel myths, but some of the myths out there are so misleading that you'll be in great trouble if I don't give you some advance warning about that. So, to begin with the neural network field, people usually always want me to start out by saying, what is a neural network? People have this question, what is a neural network? Neural networks and the neural network field have been very controversial for many years. And there are still many people who feel very threatened by neural networks. There are people in computer science and even engineering who say, gee, we don't have to imitate the brain. We're not interested in brains. This is scary stuff. We don't want to do it. And some of those folks will even say, I define a neural network to mean what I have in my local MATLAB package. When I use that in a simple-minded way. It doesn't do what I want to do, so I know neural networks don't work, so don't worry about it. But in fact, that's not a correct definition of neural nets. Neural nets are a very broad category of designs, and most of the interesting ones have not really made their way into the most widely distributed software packages. There are a few packages that are a little more advanced, but I really hope people in this course will contribute to developing new software packages which are more powerful in the area of RLADP. So, what are the general definitions that people use in the neural network field itself? There are two primary definitions. The first one I'll call the artificial neural network, or ANN. An ANN is any massively parallel design, a mathematical design, to perform or learn to perform a very general task such as optimization, prediction, memory, clustering, or pattern recognition based on distributed calculations performed by large numbers of elementary processing elements or neurons. Large, massively distributed, general-purpose computations. The examples I gave you are really the most important, but there are others. The most interesting networks are those which learn to perform complex tasks. So I'm not talking about massive parallel computing for partial differential equations, that's a different area, but this is for things like optimization, memory, clustering, pattern recognition. This is a definition of what a neural network is. So many times people reinvent neural networks. They'll say, I have a new method in control theory, and here's this massively distributed method, and it is in fact a neural network, but it's competing or reinventing things that have already been done before. And it's great when people come in and invent new designs, but it's also important to anchor them in the area where the work is being done. And this is the core of what half the neural network field is about, is building artificial neural network designs which are these large, massive, parallel computing, general-purpose designs. The other definition of a neural network, we'll call it a biological neural network, BNN, is any mathematical network design or model which tries to capture the essential information processing capability, especially learning, of brains. The neural network field strives to develop dual-use designs, designs which are both ANNs and BNN at the same time. That's what the field is working to do. And it tries to learn from natural intelligence and artificial intelligence, both, with the goal of someday replicating general intelligence at the level of the mouse brain or higher. So that's what the neural network field is, that's what a neural network is. Clearly, this is a target. Some fields are just a collection of things people did 100 years ago. The neural network field is a cross-discipline area that tries to bring people together to address this big challenge. And anybody who wants to work on this challenge wants to work with the neural network field. And it's good to work with other people who have the same goal. Neural networks are not a subset of statistics, of artificial intelligence, of control theory, or cognitive science. There are people in every one of those fields who are strong advocates. Today's science has become a bit political when funding gets involved. So there are advocates for each of these fields who will argue that, oh, neural networks are just a subset of what we do. But neural nets can't be simultaneously a subset of all four fields. In fact, the neural network field tries to bring together insights from all these fields in order to address the grand challenge that the neural network field is focused on. And each of these fields has important things to contribute, but the grand challenge is bigger than any one of these fields. And as I say, it's a cross-discipline. It's not black magic. There are people who love neural nets and hate it on purely emotional grounds. There are people who say, with neural networks, we avoid all the nasty problems we had to do with mathematics. And then there are people who say, neural networks, they're all black magic. Let's use a mathematical design instead of a neural network design. Both groups are uttering absurdities, because neural network designs are a type of mathematical design. There's a lot of solid mathematics behind them. They have a lot of very important new capabilities, but they're still part of mathematics. But because there's mathematics, there is some substance here for those people who want to be substantive. So now, let me continue this introduction to neural nets with a general overview of the history, to understand what the field is, and even to understand what a neural network is. More concretely, it's important to know a bit about the history. And you may want to look at this slide more carefully after this class. On one side, there was a group of people from computational neuroscience, people interested in neural circuits in the brain, mathematical biology. And the most famous of those people contributing to our field is a person named Donald Hebb. And when there's more time, I usually talk about the book by Donald Hebb. It's very famous, The Organization of Behavior, like Wiener's book. It's a kind of living classic, and it's more up to date than Wiener's book. It still has new things to tell us. When I hear people talk about who's the father of this field or the father of that field, I sometimes say Donald Hebb is the grandfather of the neural network field on its mother's side. The birth of the neural network field today basically occurred in 1987. There are people who say modern quantum mechanics started with the great Congress of Saclay in 1926. Neural networks is another one of these unique fields that really has a birthday. It began with a great conference. There was a lot of work beforehand, like the work I'm going to describe today, but the birth of the neural network field as a large organized discipline with its own journals and so on really came in 1987 at a meeting held by IEEE, the first international conference on neural networks. And that great event with thousands of people came about from two groups merging together. There was the computational neuroscience group interested in these brain circuits and models inspired by Hebb, and Steve Grossberg of Boston was a big part of this. The other half of the field came more from the technology, artificial intelligence side, and that's really the side that I come from. But that includes people also interested in the brain, but taking more of a mathematician's approach to it. In fact, my side of the neural network field really owed its start to the initial enthusiasm way back in the 1950s, when digital computers were brand new. And there were articles in magazines saying, electronic brains, are they brains or are they not? And the early computers were certainly nothing like a brain, you just program them. But a lot of people started to say, maybe we can build electronic brains. How do we program these things to be like brains? And thus was born the early field of artificial intelligence. There were three different schools of thought in the early field of artificial intelligence. One group of people said, I don't know what intelligence is, but I know it when I see it. So if a system can play a good game of chess or checkers, well, that takes intelligence. So a lot of people in the early artificial intelligence field focused their efforts on trying to perform specific tasks which require a lot of intelligence. There was an early checkers player by Samuels and Samuels, which used something like a critic network. For the AI people interested in reinforcement learning, the work by Samuels and Samuels in the early checker player was the starting point for them of some of their thinking. That was very exciting. The early programs were very exciting. But then as people started getting really buried into the details of specific domain knowledge, they stopped learning about general intelligence. So the early Samuels work illustrated some general principles that an intelligent system should have. But when they got around to chess, when you started having these programs in machine language code 20 pages high, more like 20 inches high, full of obscure things no human being could follow, all specific to the domain of chess, it doesn't tell you so much about intelligence in general. You run out of the benefits. So that's one stream of approach. Another major stream of approach is due to some great classic people, Newell, Shaw, and Simon, based primarily at Carnegie Mellon University. And they came up with a different argument. They said intelligence does not reside in the specific algorithm or procedures you use to solve a specific task. Intelligence is not the rules you follow to play chess. Intelligence is how you learn the rules, how you learn to behave. Specific rules are like a clamshell. They are the product of the living system. They are not the living system itself. The living system is a system which has a universal ability to solve any kind of problem, to learn to solve any problem, and it produces solutions, but the intelligence is this general problem-solving ability. And that sounds really great. That's a very sensible approach, but then as an engineer, you ask, how do I build a system to solve any problem? How can I formulate that idea in a mathematical way that I can really work on with real mathematics and real systems? And at the end of the day, there were really only two answers to that question. There are two ways of defining general problem solving that we could really implement. One concept was reinforcement learning, which I've already talked about, and that's the one that I really started pursuing. How to maximize some sort of success or reward measure over time based on learning from experience. Another approach was logical reasoning systems. How can you learn in general to prove theorems, to do logical reasoning? And way back when I was doing some of this stuff, way back in the 70s, a lot of AI had degenerated into expert systems, domain-specific systems to do abstract reasoning, typically without semantics and without meaning, just pushing words around to answer questions. And there are some uses for that. But it wasn't really moving towards brain-like intelligence. Reinforcement learning was a different approach. One of the first papers I ever saw on reinforcement learning was by Marvin Minsky at MIT. In fact, he had a classic paper in a book called Computers and Thought, a very light reading paper from way back in the 60s, Feigenbaum and Feldman, Computers and Thought, and he argued how reinforcement learning was the key to all intelligence. All we have to do is build systems which learn from trial and error, and that's it. Everything else is just emergent from there. And I spoke to Minsky about it, and he was a little embarrassed. He had a paper with Oliver Selfridge giving a very simple kind of reinforcement learning method, but he found that it really wouldn't work if you had more than 2 or 3 variables. And so he recognized that this model, which seemed very wonderful for trial and error learning, really wasn't a credible model of brain-like intelligence. It was not powerful enough. And a lot of what I really worked on in the early 70s was how do I come up with a more powerful form of reinforcement learning using mathematical principles to do it. And that's what you saw in the last chart. Learning from dynamic programming, turning that into an approximation and learning system, and that's where the first real powerful reinforcement learning system came from. So that's where I really came from. But there was another school of thought, which was the perceptron school, which is also extremely important. I even go so far as to say, while Hebb is the grandfather of the neural network field on its mother's side, the biological side, John von Neumann is the grandfather of the neural network field on its father's side, on the hard technology side. There was a meeting between John von Neumann and Warren McCulloch and Norbert Wiener, where they talked about how to build brain-like intelligence, and they agreed on the idea that we should start to build systems using a simple model of the neuron. We know brains achieve intelligence by having lots and lots of neurons connected together, learning by some general learning rule, and all of the details of what we learn seems to be the product of these neurons. So let's come up with a model of the neuron, and let's come up with a way to adapt the neurons to build a general intelligent system. There are some people who say they don't like the von Neumann approach to computing because von Neumann also did earlier work on the digital computer. And they say, we want to get beyond the von Neumann paradigm for computing. And that's a little amusing because von Neumann was one of the key people who who developed this neural network paradigm way back when. He understood the importance of parallel processing and importance of learning what we can from the brain. As a result of that earlier work, there were a lot of people like Woodrow and Rosenblatt. Woodrow is still alive and giving lectures on this stuff. He developed least mean squared training, which I described to you before. That was one of the outcomes of the McCulloch and Pitts neuron, and that's what I'm going to go on to next, because we still use this kind of neuron model even today. So the next slide describes the McCulloch and Pitts model of the neuron. And this is not just history. This is a big part of what we do today and what you guys should be implementing on your computers today. In those days, they understood that biological neurons are much more complicated than this simple model. But McCulloch and von Neumann argued that we don't need a model of the neuron to include every last ion channel. That's not how you understand the functional level of a neuron. If you want to do a model of a transistor, you can build a gigantic model that predicts every atom in that transistor, and I fund some people who do that. But at the end of the day, if you're building a digital computer, you can really understand how some digital computers work by assuming that big fancy transistor is just an AND operator or a NOT gate. And you can design digital computers accurately by just putting lots of AND gates and OR gates and putting a lot of logic on the paper. And then you implement them with transistors, which are complicated, but the real work is done by the logic, and the logic is relatively simple. And the argument of von Neumann was, and McCulloch and Pitts was, that the real logic that's implemented by the neuron doesn't seem to be all that complicated. You can capture a lot of it by modeling these essential elements. You have a cell, that's what a neuron is. You have inputs coming from things called axons, but they're just like wires coming in. On each axon there is a signal. It's a numerical signal. You can use X sub I to represent the size of the input, the size of the signal coming in along axon I. In the old days, people said, oh, these inputs are on or off. Neurons spike. The outputs of neurons are 1 or 0. Either you're spiking, sending out a spike, a discrete surge, or you're doing nothing. 1 or 0. So at each time, on each input line, there's a 1 or a 0 coming in. That was the idea then. It's changed a little. As an axon hits the dendrites, the input zone of the cell, there is a strength of connection, which is called a synapse strength, or weight. So in this model, X sub I is the 1 or 0 coming in on this axon. W sub I is the strength of connection to the cell body. The voltage of the cell, the voltage on the cell membrane, in this simple model, is just the sum of synapse strength times signal. It's the result of all of the excitatory potentials coming in here. And that's the first equation of the model, that the voltage on the cell, V, is equal to some constant, some base level threshold, plus the sum over all of these input lines of a weight times X. But then the output of the cell is not the same thing as the voltage. And in those days, the idea was the voltage is a continuous number, but the cell outputs a 1 or a 0. So the output of the cell is a simple function, S, of the voltage. And on the next slide, I'll talk about different choices for S, because those have turned out to be very important in the history of the field. It turns out there are 4 very interesting choices for this function S. In the original work of McCulloch and Pitts, the function S was assumed to be a simple step function, because back in those days people did believe in digital logic. They did believe the brain was a little bit more like a digital computer than it really is. And so the idea was to say that if the voltage is less than some limit, I'll call it 0, but if it's less than some threshold, then the output is 0. The neuron doesn't fire. But if the voltage is above that threshold level, it fires. So the output is 1 if V is greater than 0. The output is 0 if V is less than 0. If we use this choice of S, then that neuron is called a threshold logic unit, TLU. And there were lots and lots of books written way back in the 60s and 70s about neural networks made up of threshold logic units. This was the #1 most popular neural network model in those days, the threshold logic unit model. And those kinds of neural networks were called perceptrons. When I started working in this field, really in the period from 71 to 81, I proposed that we use a different model of S, which I'll talk about. I proposed that we model the neuron as a continuous logic unit, or CLU. And in that model, very similar to the old model, I made a slight change. The output is 0 if the voltage is less than 0. It's 1 if the voltage is above 1. But if the voltage is between 0 and 1, the output is a continuous number between 0 and 1, equal to the voltage. And a lot of people said that's crazy. The neuron spikes or it doesn't. What does this model mean? I'll get to that. In the modern neural network literature, people have actually taken the same principle further. I believe Steve Grossberg had a lot to do with making this happen. It doesn't really change what you can do in the mathematics, but the new version is a little smoother. And the idea is to use S as a sigmoidal function. And that's why we call it S. Some people call it the squashing function. Today, the most popular choice is hyperbolic tangent, tan H. So if you guys start programming this, I recommend use tan H. Okay? That's what you should use. That's the modern choice. It works very well. And a lot of the subroutines that you can get via this course will use tan H. That's sort of the standard choice today. The reason why we choose it is it has a nice shape, like what Grossberg has advocated from his view of the empirical data. And in addition, it has very simple derivatives. If you do local calculations, it's a cheap and easy calculation, which is important. What's more, in this version, x varies between -1 and 1. And that's not exactly biological. If you think of 0 output as -1 and maximum output as +1, well, that does map into the biology. But it turns out this just works out to be easier and cleaner. You don't have to use it. You can squash it to the range from 0 to 1 if you want. But in engineering, it turns out to be easier if you have a little symmetry here. This just makes life easier on the engineering. It doesn't really change the basic design. It doesn't change the validity of the model. It just makes it easier to compute. There is a fourth choice which is kind of interesting. You should keep in mind. What if you take as a choice S of v equals v, a linear function? In that case, the McCulloch-Pitts neuron is really just the general linear model, which is what people use in multiple regression. Okay? So it's important to remember that there are close connections between what we do in neural networks and what people do in statistics. In fact, a lot of what we do in neural networks could be called nonlinear regression. It is a special case of nonlinear regression with some special extra power added. But the mathematical validity of what we do really rests on statistical theory, which I'll talk about next week. But in the special case where you pick S of v as v, what you get back is ordinary least squares. And people use W for weights in ordinary statistics. Multiple regression, which uses the general linear model, is still the most popular method used today in statistics. If you build a very large-scale econometric model, which I've done several times, most of the best state-of-the-art models are still based on multiple regression for many reasons. It's a powerful technique. It's ordinary least squares. For those of you who are interested in doing side reading to learn more about what people really do in statistics, as opposed to what they say in some machine learning courses, to learn what people really do in statistics, one good starting point would be to read a very simple light book by Wonnacott and Wonnacott called Introductory Statistics for Business and Economics. Very light book, but the principles are really straightforward, and they're closely related to what we're going to talk about. So, when Woodrow and others proposed the use of multi-layer perceptrons, one of the main applications they were interested in is something called supervised learning. I talked about that briefly last week, but it's a very important topic. We need to talk about it in more detail. Supervised learning is a general class of problems which we address in the neural network field. 20 years ago, if you took a tutorial on the neural network field, they would often begin by saying, the neural network field gives you three kinds of learning. There is reinforcement learning, supervised learning, and unsupervised learning, which is good for things like clustering and memory. And those are still the most important parts of the neural network field today. There are much more people doing supervised learning than reinforcement learning because this is easier to understand. It's easier to map into ordinary data modeling. In supervised learning, you're trying to build a supervised learning system. A supervised learning system is a system which tries to predict desired outputs or targets based on inputs. It's kind of like dependent and independent variables in statistics. In fact, it's really the same thing. So when you do supervised learning, there's several variations. If you do it in real time, you have a neural network or some other learning system here. At each time period t, you get a set of inputs, which we'll call the vector, well, little u. I'm going to use little u this time because of all these control things. You have a vector little u that's coming in, and you're outputting something that's supposed to be a good prediction of something else called x. But when you make the prediction, you don't know the answer. You take your inputs, you guess the answer, then you find out what the answer really was, and you go back and you train your network. And then you go to the next example. Get a bunch of inputs, predict the answer, find out what the correct answer or target was that you should have hit, then you adapt your network to meet the target, and you just iterate over and over again. This is called real-time learning or observation by observation learning. Now, many times when people use this, they'll use it on databases. There was a very exciting early application of supervised learning with neural nets by AT&T Bell Labs, where they had a massive database of zip code characters, pixels. And for each observation, the inputs were the black or white code for each of the pixels in the image. The target is the correct classification of the digit. And they had examples available from the post office of thousands of handwritten digits and the correct classifications. And they would try to train the neural network offline, observation by observation, to adapt the weights so that it would make better and better predictions. And they would cycle through the data, and then after they were done, they would test this neural network on pieces of the data they never used in training. It's called a training set and a test set, which is a very important part of training neural networks. And they got a high degree of success. So that's another way of doing supervised learning. It's observation by observation, but from a database. The fact is, a lot of the methods of neural networks, you can also use them in something else called batch learning, where you look at all your inputs, you look at all the targets, and then you adapt the weights to match all of them, and then you iterate over the whole database, and then you check that against the test set. That's called batch learning. There are times when batch learning is the most practical thing to do when you've got a fixed database. There are times when observation by observation learning works faster, even with a fixed database. And people generally assume if you want to build a brain, brains do real-time learning. Although it's not as simple as you might think. But to build a brain, you need to know how to do real-time learning. In this task of supervised learning, notice it's just one vector in, one vector out, there's no memory. So in statistics, people would say this is forecasting without time series. This is static forecasting. There are methods of statistics that can be used here. There are many neural network methods for doing supervised learning. There are many structures of networks that people use for this. But in any case, one of the first questions that people were asking in that ancient history was, can we use multi-layer perceptrons, the standard form of neural networks, to solve supervised learning problems? Can neural networks learn to perform these kind of simple tasks? And we know that brains perform more complicated tasks. But first they wanted to ask, could neural networks learn to perform these simple tasks? Before I get into that, I should say something about the other networks. Multilayer perceptrons are still the gold standard in the neural network field. There are many other types you'll read about that I won't have time for today, like Hebbian neural networks, something called CMAC, radio basis functions. A lot of the Hebbian neural networks actually work better for things like associative memory. In engineering, people have frankly not found a lot of use for these networks, except in very narrow special cases. These are what we typically call local networks. You can train them quickly, but their ability to generalize for many inputs is really not very great, even when there's just a handful of inputs and a nonlinear relationship. I mentioned before there are theorems by Andrew Barron of Yale who prove the multilayer perceptron has better properties in approximating nonlinear function than any other of the standard approximators he looked at, which include local approximators, Taylor series splines, all of those things. As the number of inputs increases, multilayer perceptrons have better approximation ability. So that's why I'm talking about multilayer perceptrons today. So in my history slide, the name Minsky appears several times. Besides working on reinforcement learning, Minsky and Papert wrote a very classic book called Perceptrons. I think it was like 1969 that it came out. And this book really destroyed the early neural network field. Most people said the publication of this book was the death knell. All of these people who had been excited by McCulloch and Pitts and Woodrow, basically this book was like the funeral obituary. Bernie Woodrow tells me the field was really already dead. All the book did was just put down on paper what everybody knew and explained it. And what they knew was they were having problems. Marvin Minsky talked about the following very simple learning task called the XOR problem. Very classic problem. In this problem, there are only four examples we're trying to learn. T goes from 1 to 4, just 4 examples. We're trying to build a neural network which learns to reproduce the correct answer for just 4 cases. And in these 4 cases, the neural network has 2 inputs and 1 target. One input, x1, is like this, 0, 0, 1, 1, and x2, 0, 1, 0, 1. The target is to output the XOR function. If x1 is false and x2 is false, XOR is also false. Only if one is true and one is false do you get a 1. This function turns out to be a nonlinear function of x1 and x2. So one of the first things Minsky showed was if you have a single McCulloch-Pitts neuron, a single linear model, a single linear regression equation, you cannot represent this function. You cannot approximate it, at least not with any accuracy. You can't reproduce this function with a single McCulloch-Pitts neuron. That's the first thing he showed. Then he showed that if you use a multi-layer perceptron with one neuron, with neurons on the bottom, outputting to neurons in the middle, outputting to neuron on the top, a multi-layer perceptron can solve this problem. It can represent the function. But nobody in the 60s could figure out a learning algorithm for how to adapt the weights so that you could learn this kind of function. Basically what Minsky said was, unless somebody comes up with a learning algorithm that can solve this problem, we don't have neural networks that can even do this simple task, let alone higher order intelligence. We're dead. Now, Minsky's book said other interesting things, but this was a grand challenge. This book became so popular that for many years it became heresy to even talk about neural networks. It was an embarrassing heresy. There were people who would say, gee, we used to think that brains could work, but now we know brains can't do anything. Well, that's questionable. And there were a lot of people who said, well, look, trying to copy the brain, it's like trying to put flaps on an airplane. We don't have flapping wings on airplanes. We do need flaps on airplanes as it happens. But the idea of learning or understanding from the brain, a lot of people gave up. And there were people who said, we'll just hack our way to intelligence. We're clever. we'll just think of whatever occurs to us, and since we're such brilliant people, it'll work. Problem was it didn't. So there was a real impasse here, both in terms of finding real intelligence and learning, which people pretty much gave up on back in this time, in the mid-70s, but also in the neural network field, which became heresy. So one of my main claims to fame in this field is that I did find a solution to this problem, which is now called backpropagation. And I presented this idea really in 1971, not in a published paper, don't claim it's a published paper, to Harvard University. And I said, I have found a new general way to adapt multi-layer perceptrons. It basically involves changing the model from a threshold logic to a continuous logic unit, which I can justify, and then I have a way to propagate derivatives back with a local calculation, a purely local calculation. That purely local calculation will let you adapt all the weights and converge. And I even remember I went to ask for computer time at Harvard on the local PDP machine because I wanted to do lots of little experiments where you have like 25 pixels and you can recognize the letter C. And you can train it not only to do XOR, but to recognize simple letters. And when I presented that to people at Harvard, they said, we're sorry, but we don't believe this could work. We don't believe this backpropagation thing could possibly work. This way of calculating derivatives, we just don't believe it. You would have to prove it. What's really ironic is that there are people in the AI world who have written books saying that the guy I asked for computer time for invented backpropagation, which is totally crazy because they never met the guy, and he was the guy who said this kind of thing could never possibly work. He certainly didn't see it as part of his mathematics. I should make one other comment here about where this idea came from. Part of it is common sense for derivatives, with a chain rule for partial derivatives, which I cited in 1971. But part of it also came from reading a lot of psychology. I was trying to understand the brain, and I read some of the work of Freud. Some of the work of Freud is not very helpful here. It's very confusing. It is very domain-dependent stuff about human touch and whatnot. But Freud also had a general theory of psychodynamics, which was very interesting. Freud started out wanting to do neural network models. He had to do therapy to make money. But he retained his interest in neural network ways of thinking to his dying day. And he's written a lot of stuff on psychodynamics. How do neurons work and how do they generate the kind of complex psychology that he observed in the lab? And one of the things he said, I believe one key part of the brain is we learn forward associations. If A causes B, A in the present causes B in the future, there should be a forward axon. He talked about axons and neurons. From A to B, the strength of that connection should be the strength of the causal relation. But for every forward relation, there is a backwards flow of what he called psychic energy or cathexis. The idea is if A causes B, and we like B, then that will cause us to like A. So the energy of liking B, the valuation that we put on B, the affect on B, is somehow represented, maybe by chemicals in the cell that represents B. The flow of the chemicals back to A, making us like A, should be proportional to the strength of how much we like B, multiplied by the strength of the causal connection along the link. And that translates into mathematics. A lot of people hated Freud so much they didn't bother to notice that his idea could be translated into mathematics, and it translates into a viable algorithm. And that's basically where I got the idea. So let me run through this history a little further. But why did I think it was legitimate to do this kind of causal model? Well, when Harvard didn't give me computer time, I didn't give up. I went to Marvin Minsky, had an independent study with him. And I said, Marvin, I don't like to get into conflicts with people. How about we do a joint paper together and show that this problem has been solved? We can solve this problem by making the small change in the neuron model and using backpropagation. And Marvin Minsky said, but wait a minute. Everybody believes that neurons are digital objects. They input zeros and ones, they output zeros and ones. How can we get away with this kind of model of the neuron? People will say it's not biological. We have to follow biology. And even today, there are people who will tell you a biologically realistic model has to be one that basically outputs ones and zeros for spikes and silence. So what I said to Marvin at that time was, look at this graph. I pulled out a graph from the book by Rosenblith called Sensory Communication, 1961. Very solid book from MIT Press that they were using in my course from Charlie Grossman at Harvard. And this shows one of the key inputs to the cortex. It happens to be the olfactory bulb, but that's very much like the thalamus. You could do the same kind of thing from the thalamus. They're cortical cells like this. If you look at the time series of this, it doesn't look like square waves. It doesn't even look like random spikes at random times. What you see at regular time intervals, you see things that are called volleys. And sometimes you get a big volley, and sometimes you get a small volley. The intensity of the volleys is what carries the information. The information is really a continuous variable. It's not 1 or 0. And it occurs at regular time intervals. As I said before, this follows something called the alpha rhythm. And there are people who have unraveled the wiring of the clock pulses from the thalamus to the whole cerebral cortex, which really impose this regular rhythm. And there's more recent data by Barry Richmond of NIH really describing these kinds of information flows, the neural code they call it. And so I said, look, the real code is not a continuous variable or a random 0, 1. The real code is that at regular intervals, you get a volley representing a continuous number. So this is actually a more plausible model biologically, as well as something easy to train. And Minsky said, well, yeah, that's empirical data. But he went on to say, I know these modelers. You can give them all the empirical model data in the world. They live in their own world. It will take them decades to even tolerate this kind of thing. And I have to say he was right. So then I went back to Harvard. And as I said before, the response at that time was we didn't believe in neural networks. Nobody did. And they really wanted proof. It's entirely legitimate that they wanted proof. Is this kind of backwards flow going to give you correct derivatives? They wanted proof before they would believe it and grant a Harvard PhD. And so I decided that's legitimate. I will live up to what they ask for. I will make a proof. And that's where the chain rule for ordered derivatives comes from. The chain rule for ordered derivatives is a universal theorem. It's a new way to calculate partial derivatives. It is different from the conventional chain rule for partial derivatives. The conventional chain rule for partial derivatives basically does not tell you how to calculate the derivatives of the output of a complex dynamical system with respect to the inputs. I don't know if you've ever been in the position of trying to work your way through a 20-equation econometric model. Here are the inputs, here are the outputs, and you want to calculate the derivative of the output with respect to the inputs. If you use the ordinary chain rule, you will quickly become somewhat confused. And you will suddenly realize you're making arbitrary judgments. It's pretty scary. If you want to do a reliable job of solving that problem in econometrics, you need to know the chain rule for ordered derivatives, which I'm going to try to describe to you today, though it may go to the next lecture. So what I did for my PhD thesis was I formulated this general theorem and I proved it directly. It only takes about 3 pages of general mathematics to prove this chain rule, which is universal and flexible for use in any complex nonlinear differential system. It's not only for neural networks. But it did start with neural networks. So let me put it in more general form on this slide. Okay? The chain rule for ordered derivatives gives you a general rule for how to calculate the derivatives of any scalar result with respect to all of the inputs and all of the weights in a nonlinear differentiable system. This could be feed-forward or recurrent. You can do this for PDE solvers. You can calculate the derivatives of a large PDE simulation code using backpropagation. The details of that mathematics are described in more detail in a paper I have up on the web that was published in Automatic Differentiation 2004. I gave you the citation earlier. It's a complex history. I won't go through it all today. I can say that I discussed this with people in Oak Ridge back when I worked for the Department of Energy. They began applying it to partial differential equation codes, and they decided to give it a new name at that point. They called it the second adjoint method and reverse differentiation. But in fact, it came from Oak Ridge, which in turn came from our discussions, which came from the earlier papers which developed this general theorem. A lot of the details are in my PhD thesis, which came out as a book, The Roots of Backpropagation, where you can see the early applications. The first real-world application was to estimating a complicated time series econometric style model used in political forecasting. Just this past year, one of the leading econometricians got a Nobel Prize for going past multiple regression and using something called mixed vector ARMA models for use in real-world econometrics. That was not possible until we found a way to calculate the derivatives of those models to be able to tune the weights. And that was one of the things that was achieved for the first time in this PhD thesis. I put together a program in the time series processor package at MIT, which went to the Federal Reserve Bank. So that was really the first application of backpropagation. Let me go on a little bit more. Okay. When people used the simple multi-layer MLPs of the kind that Minsky talked about years ago, they would always get into questions. How many hidden nodes do we have? How many layers do we have? There is a much more general form. All of those choices are a subset of that general form. So my first small contribution to the new software package in MATLAB at CLION is a subroutine that implements something called a generalized multi-layer perceptron. And I have this in several papers. It's in that book I just mentioned. And the generalized MLP, you have a string of neurons, 0 to m. Well, 0 is an intercept term, just a constant, 1. You have m inputs. We call them neurons, but we just pass on the numbers. And then we have live neurons. Each neuron gets to take inputs from all the preceding neurons. So this is a really connected network. Totally connected. If you don't train it the right way, having too many weights will bog down your system. You don't want too many connections. But there are modern ways to train neural nets that overcome that bottleneck problem. So this is the most general form, and it can learn which connections are important and strengthen those. So we have a subroutine that implements this kind of neural network. One reason I like to show you the general network is that the equations are much simpler for the general case than they are for the special cases. These are all the equations. The subroutine for the generalized MLP is a very short and simple subroutine. Basically, for the first m neurons, you just read in your inputs. For all the active neurons, for each neuron in order, you first calculate the voltage as the linear sum. And you'll notice it starts from 0. The trick is that x sub 0 means 1. That's just a faster computer code. And then you go through the squashing function, which is hyperbolic tangent in our case. And then you just read it out. You just iterate through this sum and this function for each neuron, and then you're done. The real question is, how do we calculate the derivatives of this system? How do you work your way backwards to calculate the derivatives? And to explain that, I have to explain what an ordered derivative is. And I'd like to give you a simple example of what is the chain rule for ordered derivatives. Now, since this is a new mathematical method, you might need to practice a bit. So let me emphasize, if you go to the Handbook of Intelligent Control, Chapter 10, which is up on the web, there are examples you can work through. I also published some examples way back in 1987. In 1987, the Department of Energy asked me to program the official model of oil and gas. And in order to make it work on timing and budget, we had to use backpropagation. We had to use the chain rule of ordered derivatives to calculate the derivatives. And that paper was published in IEEE Transaction System Managed Cybernetics, giving the example of the econometric model and how we use the chain rule for those derivatives. In this simple example, I'm assuming we have three variables. What a derivative means is the impact of changing one variable on another variable. So if we have a simple dynamical system where Z1 affects Z2 and Z2 affects Z3, but Z1 also has a direct effect on Z3. That's a good example of impacts in a dynamical system. If we have a function which describes Z2 as a function of Z1, and another function which gives Z3 as a function of Z2 and Z1, we know how to differentiate those functions. The partial derivatives of those functions are the ordinary partial derivatives. But if you want to compute the total impact of changing Z1 on Z3, you have to add up two terms. There's the direct impact of Z1 on Z3, which in this example is 4. That impact is part of the function which defines Z3 as a function of Z1. But there's also the indirect impact. By changing Z1, you change Z2. By changing Z2, you change Z3. You won't see that if the only thing you look at is the function that gives Z3 as a function of these two. So in this case, the total order derivative, the impact of Z1 on Z3, is the sum of two terms, these two terms. This is the direct impact here, 4 in this example. But then you have to add this impact multiplied by this impact, which is 3 times 1 in this example, giving you a 7. So the total order derivative, the total impact of changing Z1 on the final result, is the sum of the direct term plus the indirect term. In the general case, the order derivative of an outcome with respect to any one of the inputs is the sum over all the things in between of the order derivative of this guy with respect to those earlier things times the ordinary partial derivative of the in-between thing on the earlier thing. That's the intuitive meaning of this equation. So this tells you, if you want to know the impact of this early thing on the later thing, first you compute the order derivatives of all the guys in between. And then for each one of those, you multiply this order derivative by this simple ordinary partial derivative. Okay, so you may need to study that a little, but you can apply this directly to the example I just gave you. If you apply this to the forward equations of the multi-layer perceptron, you end up with these equations to work your way back through the system. These equations tell you how to calculate all the derivatives. And you'll notice, calculating all the derivatives costs the same as running the model in the first place. They're all local communications, local calculations. If you were using a massively parallel processing system, these things are also parallel, the same way as the model was to begin with. Like the neural network itself, it is local and parallel. You input derivatives from upstairs. You need to know the derivatives of error with respect to your output. And then working your way back from the last neuron all the way to the beginning, for each neuron, you calculate the feedback to that neuron. That's the order derivative of the of your error, really, with respect to the output of that neuron. And you just work it back. And then you work your way from the output of the cell to the voltage of the cell. I like to use this notation F underbar for order derivatives, because when you're writing a computer program, in most computer programs you can't write squiggle D plus over fraction. That's not what most computer programs like to see. And so the way I indicate an ordered derivative when I'm writing subroutines is I just use the letter F to indicate this is the ordered derivative with respect to the target I'm interested in with respect to this input. And that's how this works. Now, you might then go on to ask, what does this have to do with dual subroutines? Well, instead of implementing the calculations this way, I can do it with a subroutine. In the beginning, if you're minimizing square error, you first calculate the derivatives of error with respect to your output. In this case, I'm using y to mean your output. Sorry for the change in notation. And that's just the difference between your output and your target. Just the error vector. And then you have a subroutine, the dual subroutine, which I call F underbar GMLP. This dual subroutine has several outputs. It'll give you the derivatives with respect to all the weights and all the derivatives with respect to all the inputs. So you have multiple outputs from that subroutine. So when I write it as an equation, I'll put in a subscript W to say use these outputs of the dual subroutine. So the derivatives with respect to the weights come out simply by calling the dual subroutine. And what does the dual subroutine do? It calculates these derivatives, which mathematically are equal to this. The dual subroutine basically is a subset of the equations you had here. Okay? So that is the mathematics of how to do backpropagation. I've shown you how to do the dual subroutine to calculate all the derivatives. You know how to do least mean squares. And now you are ready. You should be able to implement all these things yourself. But there's an important caveat. In the real world, we don't just use least squares directly, and we don't just use derivatives and learning rates in a simple-minded fashion. This stuff can work, but if you want it to work quickly, there are certain tricks, and you need to know something about statistics. So next week I'm going to talk about statistics. Statistics is important to reinforcement learning and to optimization just as much as it is important to multilayer perceptrons. So next week I'll talk a little bit about statistics and how to make these things run a little faster than what I showed you. Thank you.